Hi everybody! So, winter is here and it's getting cold. I mean, if you happen to live in the southern hemisphere, of course you're going into your summer. But I don't. I live in England and it's getting cold, and it's getting cold in a lot of the northern hemisphere. Now you might remember this stuff here. We bought this a while ago and it's a graphene, apparently. It says contains graphene. Electrosmog paint. It's brilliant for electrosmog, but even more useful for making heaters. You can make a whole range of heaters from this kind of material, including paint on the wall heaters and clothing heaters and pad heaters and just a whole range of heaters that you can make. And because you can do that, we're going to make some heaters. And of course, the minute you start playing with electricity, you're going to get a whole load of people, safety Sallies, moaning at you. So, to protect me, this is for information and educational purposes only, and anybody who follows any instructions or any suggestions does so at their own risk. I'm doing this for experimental purposes. Right, now we're going to do something on heaters, and what I first thought was to take apart some commercial heaters. The reason for that, it'll give you an idea of what you need to do when making a heater.
Keep burbling on about how inside these things is super simple, and really I'm asking you to believe me, but I thought what I would do is take one of these things apart so we can see how super simple it is. Now the first thing to notice is, even though it's a heater, the entire case is made out of plastic. It's made out of plastic because it's just not going to get hot enough to melt the plastic, otherwise of course you'd set your house on fire. In the UK we have these kind of plugs. Every plug in the UK these days comes sealed to the wire, and it has a fuse in the plug, so it comes already fused right there. If we undo the case and take the front off, there we go, we can see what's in there. If we look at this, what we've got is a fan speed control there and a temperature control there, and of course a little LED to tell us it's on. If we look at that front again, the fan control is right there going directly to the motor, and this heat control is here, which is a bimetallic strip thermostat. Really simple thing, and we've done stuff on that. Basically the metal bends differently depending on the heat, and if we turn that up we separate it out further so it's got further to bend. That's how they work, and that of course goes straight to the heating element. So that's what's in this section here. Let's take this section apart. Okay, that's it out of its case. Let's follow that through. That's the plug that plugged in with its fuse, coming down to two wires, a brown and a blue. There's only two wires because it's what's called a class 2 piece of equipment. It doesn't need an earth. It's an entire plastic body and you can't touch it. So it's only got two wires coming in. The brown is obviously the live and the blue is the neutral. Now neutral is really easy to follow through because it gets connected to everything. I've cut this wire off to get the motor out. There's the motor there, and the motor's pretty independent from the heater actually. So the motor was connected to the neutral, and it's a squirrel cage rotor which you see in fans all the time because they're low torque, high speed and very simple and cheap to make. So the neutral gets connected to the motor, neutral gets connected to the LED, neutral gets connected to the heating element right there. That neutral goes through this. This is a bimetallic strip, and that acts as a thermal cutout switch. So we've got a thermal cutout, a very simple one, right there on the neutral. Now when the live comes in, the live actually goes to the thermostat. And this is a bimetallic strip thermostat, just like the ones you find in your cooker. So there's a little strip there that heats differentially, bends the metal open and closes the switch. That bit there you twiddle, and that is the bit that presses on that strip, meaning that it's more open or more closed or has further to travel, and if it has further to travel, of course it needs to be hotter to travel. And that controls the live. The live then comes into this section here. This is the motor switch, which also acts as an on-off switch for the heater element. The motor clearly then goes here on the live where it's connected, and the live is bridged across to an LED, which is the one that we see. After it comes through the thermostat, of course, it goes into the motor controller. These two wires are live wires going to that resistive heating element because that's the on-off switch bit, and that's the input bit that we've got there. So the motor is completely independent. It's on off, and with the speed control in here. The heater is another separate piece. It gets its live feed from the on off switch, and it's neutral through a direct connection to the neutral through this
thermal cutout switch right there. Now, interestingly enough, on the heater, we have yet another thermal cutout switch right there. So the neutral connects these two bits here. If we look there, there are two lives going in, one to the top, one to the bottom, because it's two heating elements. That's one, that's two, and they're connected to their own live. That's the actual heating element itself. And this is just a coil of nichrome wire connected here in the thermal cutout. So I've removed the wiring loom now, and those are the components. We've got a thermostat, we've got a motor, we've got a thermal cutout switch, and we've got a fan speed switch, and then of course the heating element itself, which contains another thermal cutout and a diode.
So that was a 1 kilowatt heater. These coils are about 56 ohms each. It's going to be on a 230 volt supply, but remember we're cutting that by half because of the diode, and so we're going to draw about a kilowatt or so there at that voltage. And it's really simple. I mean, we've got a fuse in the plug, certainly. Then we've got the heating element itself, motor which was to drive air over it, and the main components are these cut-off switches, which are bimetallic strips for thermal cut-off. That's all there is to this heater. Okay, I've got a toaster. Let's take that apart.
Once we get that gubbins off, this is what we get. And these are the heating elements. And this wire, well, they're identical. They're both Kanthal wire. Only difference here is, remember, this is 56 ohms. These are 22 ohms per layer. But that's all the difference there is to it. Now, the other difference is there's no thermal cutout. And, of course, it has this little circuit here. The job of this circuit is a timer circuit. You pull the plunger down, it closes those two contacts connecting live and neutral, and then there's a little timer that you bleed off with that set resistor, and it turns that solenoid off. There's a spring, it all pops up, and your toaster pops up. That's to control the timing of the toaster. It's got nothing to do with the heating, and there are no thermal cutouts here. Okay, we connect that straight up to a DC power source, like my power supply or an 18 volt battery. It draws 3/4 of an amp, and actually that's really quite nice and toasty. So we've made ourselves a little hand warmer from a broken toaster. And actually it's a little bit too warm. What we'd really want probably is about 12 volts, maybe even 6.
Okay, I took those apart really to show you how simple product actually was. I mean, that toaster is a £5. So how much effort and material do you think they're going to put in for something that they're going to charge a £5 for? Mostly manufacturing cost is about 1/4 of retail cost. So it cost £1.25 to make that toaster. The steel was like tissue paper. You could cut it with a pair of scissors. And they all use nichrome because that's the cheapest and the most available. It's on a sheet of mica. The other heater, there we go, is on a little ring of mica. So mica is almost universally the support for these things, and the control electronics is invariably ridiculously simple because it has to be. They put in the minimum requirement to make sure it's safe for you. It turns out with a toaster, that's a fuse in the plug. With a fan heater, that's a fuse in the plug and a couple of thermal cutout switches. Now, I get a lot of comments about people saying, oh, you need this, 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 this. You don't. It's astonishing how simple you can make a thing. I mean, okay, we can go to town on it. I mean, that just used a simple bleed resistor in the toaster, but we could put a 555 timer circuit in there, or any other kind of timer circuit, and I have seen toasters with optical control, where they measure the darkness of the bread and pop it out when it's the right shade. That, well, you're going to pay an awful lot of money for, and so people don't buy them, which is why you get these simple machines that work really well, but they're sold by the absolute bucket load. I wanted to add, if you've never done anything like this before, without being rude, be extremely reticent about listening to people on the internet. Most people on the internet just are stating opinion if it was fact. If it were me, and this is what I do, just have a look and see what they actually do. When you look at what they actually do, then remember that's had years out there in the public with people suing them right, left and centre if they can, so they've done what needs to be done. And if you're looking at things like car seat heaters, glove heaters, hat heaters, clothes heaters, vivarium heaters, heating mats, all that sort of stuff, you're just not going to find anything in there more than a heating element and an attachment to a battery. And if you're listen to people. Sometimes they really are talking more about their fear and their opinion rather than what you need. If you want to know what you need, well, just check out what people have been doing in actual product. It's going to be a much better guide. If you're designing something for yourself, then put in safety features and all kind of features if you want to. But if you just want to get something to work, then it is really surprisingly simple. Now, you saw me touch that at 18 volts, because 18 volts isn't going to go through you. It takes about 50 volts plus to get through the resistance of a human being. So 25 volts, really, don't worry about it. It's not going to get that hot either at something like that. So you've got very little you need to do with a thing like that, and it is on a pretty firm surface. If you were sitting on it, you're probably going to crack that mica. So you might want a fuse in it if you're running it off a battery in case you short those out, in which case they will get hot. But a simple fuse, say 1-2 amps, is going to take care of that. But normally with these kind of things where I've done heaters where they've been encapsulated like this, I don't even bother with a fuse because there's absolutely no point in bothering with the fuse. I also don't bother with the temperature controller because the rate at which it gives out the heat and the rate at which you can heat it is so low that it's extremely unlikely, I mean impossible, but that's actually going to get particularly hot. Now I wanted to show you how simple they were, particularly in product, how you can do the barest minimum to get something to work, and if you really want to, of course you can go to town on it. It's really up to you. Anyway, I hope you enjoyed the video. I hope it opened an eye or two about some of this stuff, and thank you very much for watching.